the data that we get will consist of the position of the free end of the rubber band. Again, as we stretch the rubber band along the ruler. Remember, the rubber band is measured along the ruler as it stretches. So get my arm out of the way there, but you understand what's going on there. That's the stretch. That's the position of the free end of the rubber band. You'll have the other end taped or somehow fixed, and you're just measuring this end. And the position of the pendulum string along the meter stick. So we have the meter stick, we have the pendulum string crossing the meter stick at different points according to how much the pendulum, the rubber band is stretched out. So we have these positions. Now we also write down our data. The no force position of the free end is 2.1 centimeters, so that the displacement goes back to the 2.1 centimeters. A 2.3 centimeter position would then correspond to a displacement of 0.2 centimeters. 2.7 and 3.2 from 2.1 would give you displacements of 0.6 and 1.1 centimeters. The pendulum string, the position has to be compared with the equilibrium position when the pendulum is simply hanging freely with no force pulling it over. Let's say that that is 28.3 centimeters and that the pendulum positions are 27.4, 25.4, and 22.9 centimeters. The absolute value of the pendulum displacement then from 28.3 to 27.4 is negative 0.9 centimeters, but we're not interested in whether it's positive or negative. That just depends on which way we've turned the meter stick. We're just interested in how much displacement. It's 0.9 centimeters. From 28.3 to 25.4 is 2.9, and 28.3 to 22.9 is 4.6 centimeters, assuming I've done my arithmetic correctly. Check me on that. So we have the stretch of the rubber band. Okay, how much is the rubber band stretched in pulling the bottle back, or whatever we're using for the pendulum weight, and pulling that back, and how much is the pendulum displaced. That's at the x prime position. And then we can easily calculate the force, which is just the displacement of the pendulum divided by the length. Length we're going to say is 80 centimeters. That's our L prime down to the meter stick, times the 9.8 Newton weight of the 1 kilogram mass. So, okay, we've indicated that L prime is 80 centimeters, M is 1 kilogram up here. And then we get our force. And we can easily calculate that, and then we calculate a force for every pendulum displacement, and that force will be associated with the stretch. So that if X represents the stretch, and F, of course, represents the force, we will get a graph of our data points. Hopefully that graph will be pretty much linear. Now we'll see an actual graph in the next frame.